complex zeros, and the fundamental theorem of algebra. So another theorem that will help us here is the conjugate pairs theorem. Let f be a polynomial function whose coefficients are real numbers. If a plus bi is a zero of f, the complex conjugate a minus bi is also a zero of f. And the same is actually true of irrational conjugates. Then the fundamental theorem of algebra says if we have a polynomial with degree n is greater than or equal to 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. Other ways of saying this, every polynomial function of degree n greater than or equal to 1 has at least one complex root. And another alternate way of saying this, every polynomial function of degree n greater than or equal to 1 has n linear factors. So we have a polynomial function, f, which has degree 5, and we're told it has zeros at 0, 1, 2, and I. Let's find the remaining zeros. Okay, so it has degree 5, so it has exactly 5 zeros. We have 1 at 0, we have 1 at 1, we have 1 at 2, and we have 1 at I, and I is complex, so we know it must have a 0 at the conjugate of I, which is negative I. And now we have 5 zeros, and so negative I was the remaining 0. Now we have them all. A polynomial function f has degree 5 and zeros at 1 with multiplicity of 3 and 1 plus I. Find the remaining zeros. And then, once we find those zeros, find a polynomial function with real coefficients having the given degree and zeros. Okay, so degree 5 means we have 5 complex zeros. We have 1, but it has multiplicity of 3, so that counts as 3 zeros. We have 1 plus I, and that's complex. It's our 4th zero, but we know we must also have the conjugate of that 0, so we must have 1 minus I, and that gives us our 5th 0. So those are all of our zeros. Now we need to find a polynomial function with real coefficients having degree 5 and those zeros. So we will build it by forming the factors. So the 0 at 1 gives us x minus 1. Multiplicity of 3 means I have that factor 3 times, so to the 3rd power. And then I have a factor of x minus 1 plus I, and I have 1 plus I in parentheses. And I have a factor that is x minus 1 minus I, with 1 minus I also in parentheses. We need to multiply these out, which sounds easier than it is. First, I'm going to actually get rid of those internal parentheses by distributing the negatives. So we need to multiply out x minus 1 quantity cubed times x minus 1 minus I times x minus 1 plus I. And I'm going to choose to multiply those last two terms first to get rid of my i's. So x times x is x squared, x times negative 1, x times I, negative 1 times x, negative 1 times negative 1, negative 1 times I, negative I times x, negative I times negative 1, and negative I times I. Let's simplify this. We know that I squared we can replace with negative 1. We have IX's that will cancel out. We have I's that will cancel out. So we will end up with x squared. I have minus 2x, and then 1 plus 1 is 2. So we now have x minus 1 quantity cubed times x squared minus 2x plus 2. Okay, so I'm going to write it all out without exponents. So x minus 1 times x minus 1 times x minus 1 times x squared minus 2x plus 2. I'm now going to choose to multiply these first two together. When I do that, I get x squared minus 2x plus 1 times x minus 1 times x squared minus 2x plus 2. So I'm just trying to do one multiplication at a time. Okay, going on to the next slide, just rewriting what I had. I am now going to multiply these last two. Again, we could have done it either way. I could have multiplied the first two. So multiplying out the last two, I get x cubed minus 2x squared plus 2x minus x squared plus 2x minus 2 times x squared minus 2x plus 1. Simplifying that second parentheses, we get x cubed minus 3x squared plus 4x minus 2. So we have one last set of multiplications to do. Multiplying everything out, this is what I get. So I multiplied all 3 terms in the first parentheses by all 4 terms in the second parentheses. Combining my like terms, I get f of x equals x to the 5th. Combining my x to the 4th, I get minus 5x to the 4th plus 11x cubed minus 13x squared plus 8x minus 2. So this is our polynomial function with real coefficients, having degree 5 and the originally identified zeros. This is complicated, as in you need to really be focused on what you're doing. It is very, very easy to make a little mistake. It could be a sign, it could be writing down a coefficient incorrectly, but it can completely mess up your answer here. So just be really focused on what you're doing when you're multiplying these out. Okay, here's another example. F of x equals 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. We know we have a 0 at 3i. We want to find all of the remaining zeros. Okay, so we know we're going to have 4 zeros because our degree is 4. We know we have a complex 0 at 3i, so we must have its conjugate at negative 3i. So these are 2 factors, x minus 3i, x plus 3i. But we need to find all the remaining ones. So a way of doing that is to take those 2 factors and multiply them. Okay, simplifying, we get x squared plus 9 when we multiply those 2 factors. So to find our remaining factors and then consequently our remaining zeros, we can take our original polynomial function, 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18, and divide it by x squared plus 9. Because x squared plus 9 is a quadratic factor, we need to use long division. So setting up long division, where I'm dividing 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18 divided by x squared plus 9. I did put in a 0x as a placeholder. What times x squared gives us 3x to the 4th? 3x squared. Now I'll take 3x squared and multiply it by my divisor, and I get 3x. Oops, and I wrote that wrong. Let me fix that. It is not 3x squared. It is instead 3x to the 4th. Okay, so now we're going to subtract everything, so I will change all its signs and add going down. My x to the 4th cancel out. I have 5x cubed minus 0x cubed, which is 5x cubed. I have 25x squared minus 27x squared is minus 2x squared. And I will bring down the 45x. Now x squared times what gives us 5x cubed? Plus 5x. I will take positive 5x and multiply it by my divisor, and I will get 5x cubed plus 0x squared plus 45x. I'm going to subtract these, so I will change all the signs and add going down. My x cubes cancel. I have negative 2x squared minus 0x squared is negative 2x squared. I have 45x minus 45x cancels. I have 0x. I will bring down the minus 18. Now x squared times what equals negative 2x squared? That would be negative 2. Multiplying negative 2 by x squared plus 0x plus 9 gives me negative 2x squared plus 0x minus 18. I'm going to subtract. I will change all the signs and then add going down. So my x squares cancel, my x's cancel, my constants cancel. And I have a remainder of 0. So when I divided my original polynomial by x squared plus 9, my quotient was 3x squared plus 5x minus 2. So now I know I have these original two factors that I found times 3x squared plus 5x minus 2. But that last factor can be factored further. So let's factor 3x squared plus 5x minus 2. I'm going to use the x box, so I need to multiply 3 times negative 2 and put negative 6 at the top, put 5 at the bottom. Numbers that multiply to negative 6 but add to 5 are 6 and negative 1. So filling in my box, my first term goes in the top left, my constant goes in the bottom right. I'm going to put the 6x here and the negative 1x here. In my first row, my GCF is 3x. In my second row, I will factor out a negative 1. 3x times x gives me 3x squared, and 3x times 2 gives me 6x. So that factors to 3x minus 1 times x plus 2. I already had x minus 3i times x plus 3i. So I have 4 factors, 4 linear factors. And my zeros, I already know 3i and negative 3i. And I need to set the remaining factors equal to 0. So 3x minus 1 equals 0, x plus 2 equals 0. Let's solve for x. So x is 1/3, and x is negative 2. So I have 4 zeros, 3i, negative 3i, 1/3, and negative 2. Find the complex zeros, then write in factored form. F of x equals x to the 4th minus 1. Okay, so now this one's a little simpler because we don't need to go through quite as many steps as we did in the last one, because this is actually a difference of squares, and we can partially factor this. So we have 2 sets of parentheses. The square root of x to the 4th is x squared. The square root of 1 is 1. 1 gets a plus, 1 gets a minus. And then I can factor the second set of parentheses again because it's a difference of squares again. And we get x plus 1 and x minus 1, and the x squared plus 1 comes down. So we're finding the complex zeros. So I'm going to set our zeros equal to 0. So our factors equal to 0 and solve for x. So here we get x is equal to plus or minus I. X equals negative 1. And x equals 1. So the zeros are 1, negative 1, I, and negative I. Now I did factor it, but I don't have linear factors. So if I needed to write my linear factors, f of x equals x minus I times x plus I times x plus 1 times x minus 1. So that's completely factored with my 4 zeros. And I know I have all my zeros because the degree was 4. Find the complex zeros, then write in factored form. F of x equals x to the 4th plus 2x cubed plus 22x squared plus 50x minus 75. the degree is 4, so the total number of zeros is 4. Using Descartes' law of signs, I have one sign change, so the number of positive real zeros is 1. Okay, finding f of negative x, substituting in negative x for x, and simplifying, we get x to the 4th minus 2x cubed plus 22x squared minus 50x minus 75. I have a sign change here, a second one here, and a third one here, and that's it for sign changes. So for negative real zeros, I have either 3, or subtracting 2 from that, I get 1. So 3 or 1. For my p's, to use the rational root theorem, my constant is 75, so my factors of 75 are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. My q's are my factors of 1, which are plus or minus 1. So my possible rational roots are plus or minus 1, plus or minus 3, plus or minus 1, plus or minus 5, plus or minus 15, plus or minus 25, plus or minus 75. Basically my p's, because our q's were plus or minus 1. All right, so now we are going to need to use synthetic division to find a possible rational root to help us. I'm going to try to factor x minus 1. So see if 1 is a root. And I'm going to use synthetic division. So I've set up my tableau using the coefficients of my original polynomial. We're going to test 1. So I'm going to bring down my 1, multiply 1 times 1 is 1, add going down 2 plus 1 is 3, 1 times 3 is 3, add going down 22 plus 3 is 25, 1 times 25 is 25, adding 50 plus 25 is 75, multiplying 1 times 75 is positive 75, adding I get 0. So I have remainder 0, which means 1 did indeed work. Again, it's often the case that when you don't know the answers, you're going to have to go through this a series of times to find a root where you get a 0 remainder. So I can either factor my polynomial that is my quotient, or let me show you going through and doing synthetic division again. So I can use 1, 3, 25, 75, which is from here. And I'm going to choose another number from my possible rational root list. I'm going to choose negative 3. Because remember, we had actually more possible, since we already found our one positive rational root, we know that all of the remaining rational roots would be negative. So we wouldn't want to try any more positive ones. So the first number comes down, then I'm multiplying negative 3 times 1 is negative 3, adding I get 0, negative 3 times 0 is 0, adding I get 25, negative 3 times 25 is negative 75, adding and I get 0, which means I have remainder 0, negative 3 is another rational root. And now I'm left with x squared plus 25. I could solve this factor or find the zeros by setting the factor equal to 0 and finding that x equals plus or minus 5i. So now I know my 4 zeros are 5i, negative 5i, 1, and negative 3. Those are my zeros. Now I need to write it in factored form. So f of x equals x minus 5i times x plus 5i times x minus 1 times x plus 3.